Alright, covalent bonding unit. This is screencast 2. We're going to be talking about how to draw Lewis structures for molecules. Essential questions for this unit is how can you predict bonding behavior of an element, and how do you draw Lewis structures of covalent compounds? And Lewis structures are diagrams that will represent the molecule and show the bonding between atoms in that molecule. So take a look at these two organic compounds, and you can pause the screencast and look at if you notice any bonding patterns for hydrogen, oxygen, nitrogen, and carbon in these structural formulas. Pause it. Okay, so let's look at the structures. If you notice, carbons tend to make a long chain, okay, in both of these. And then there's some other elements that are sometimes in the middle. So when you see multiple carbons in a formula, you should think long chain. Okay. But if you notice, how many bonds does carbon make? It makes 4. Huh. Hydrogens? They only seem to make 1. Each of these lines, by the way, represents a bond. If you go over here, how about nitrogen? Nitrogen makes 3. And then oxygen makes 2, and sometimes double bonds. Both of those lines mean there's a double bond in there. And one bond is a pair of electrons. You do need to remember that one, having difficulty. Okay, so remember, one bond is 2 electrons, a pair of electrons. And remember, electrons like to travel in pairs because of that orbital. They're 2 electrons to an orbital. This all relates back to that. Okay, so you can remember the HONC as the 1, 2, 3, 4 rule. Hydrogen makes 1 bond, oxygen 2, nitrogen 3, and carbon 4. And if you just look at nitrogen's electron dot real quick, hopefully you can see that there are 3 spots for nitrogen to make a bond in. Okay, so I just explained that. Hopefully you can see that the empty spots, the spots that the electrons I need to fulfill that octet rule, are the empty spaces, so to speak, in the electron dot symbol. Okay, so what do we hope to learn? That the number of unpaired electrons equals the number of bonds that are going to form for that element. And that we can draw an electron dot structure for fluorine and phosphorus, and how many bonds you predict, how many bonds it'll form. So pause, draw those 2 electron dot structures, and answer that question. Okay, so you should have your own drawing. If I look at fluorine, 1, 2, 3, 4, 5, 6, 7, and phosphorus, 2, 3, 4, 5. Hopefully you can see that fluorine is going to form 1 bond. Phosphorus has these 3 empty spots, is going to form 3. Now, even though we've talked about how to draw these electron dot structures, when we start drawing Lewis structures, those electrons don't necessarily have to stay in those same locations. When you put 2 elements together to form a molecule, you draw their symbols next to each other, and those electron dots may have to move a little bit, still keeping the sides, the 4 sides to the element, but kind of rearranging so that you can pair up those electrons as needed. Right. Okay. And these are what Lewis structures look like. It's a structural formula that includes all of the valence electrons for that molecule. The ones that you will be asked to draw are really the Lewis structures. I want to see these unshared pairs. Okay, this is a water molecule. It shows these electrons being shared between the oxygen and the hydrogen. Notice the symbols for the elements are about the same size, and the electrons that are being shared in that bond are drawn between them. Okay. These are 2 electrons that are being shared between the oxygen and the hydrogen, and that's how they are shown. You can use different symbols so that you keep track of whose valence electrons are whose. one of the common mistakes, kids kind of just throw in extra electrons. You can't do that. You are limited to the number of valence electrons, or if there's a charge on the polyatomic ion, we'll look at those later. Okay, but for now, when we're talking about a neutral molecule, you're limited to the number of valence electrons that each element brought in. Okay, these pairs need to be shown. These are called unshared pairs because they're not shared. So these are unshared pairs. Okay. You can also represent, instead of drawing 2 electrons, you can draw a dashed line. This represents those pair of electrons that's in a bond. Do one or the other, don't do both. Structural formulas don't show the unshared pairs. You are going to be asked to draw Lewis structures. I don't want structural formulas, I want Lewis structures. I want to see these unshared pairs. Those are required. Okay, so bonding pair. Pair of electrons shown in a covalent bond shown between the 2 atoms. Lone pair or unshared pair. Pair of valence electrons not involved in the bonding within a molecule. They belong to just one atom. Okay, 2 goals when drawing Lewis structures. Each atom should have a full valence shell. That means hydrogen, helium, well, helium's really not going to bond, but hydrogen should have 2. Okay, so each atom should have a full valence shell. Use only the number of valence electrons available from each atom. Don't add or subtract to make the structure work. You really are limited to the number of valence electrons. Okay, so how do we go about doing this? There are 2 approaches. We're going to go through one, and then we're going to look at another. All right, you decide which one works for you. The goal is to come up with a valid Lewis structure at the end. So we're going to use this compound, CH3I. The first step is to determine the total number of valence electrons in the structure. Carbon has 4, 1 carbon, so 4 electrons. Iodine has 7, and I have 3 hydrogens, each with 1. That's 3 electrons for a total of 14 valence electrons. Sketch the Lewis structure for each of the atoms to determine how many bonds each will form and how many lone pairs they will have. Typically, the atom that wants to make the most bonds is the one that goes in the center. Okay, so typically, atom that wants to make the most bonds goes in the center. Do not think of chains or rings or anything like that. Most often we're going to have one atom in the center with things stuck around it. All right, one atom in the center, things stuck around it. So I got carbon, 4 bonds, no lone pairs. Iodine's going to make 1 bond. Hydrogen's going to make 1 bond. Hopefully you can see that carbon's going to go in the center. Okay, and this forms the skeletal structure. The element that wants to make the most bonds in the center, and then the others on its 4 sides, if there's 4 being bonded to it. And then you draw lines to represent each bond. Each of these lines represents 2 electrons. You can also draw the individual electrons using different symbols. Next step is to add the lone pairs so that all atoms have a full valence shell. Count the electrons to make sure that the number of valence electrons equals the number of available. So I have those 4 bonds, each has 2 electrons in them for 8 electrons, and I have 3 lone pairs for 6. I end up with 4 electrons, which is what I started with. Let's look at another approach, and this is a little bit more systematic. And we will use the same compound, which is CH3I. The first thing I'm going to do is calculate the number of electrons needed for a full valence shell for each atom. Alright, so I have carbon, I need 8 electrons. For the 3 hydrogens, I need 6 electrons. And for the iodine, I'm going to need 8. Okay, that's how many they need for a full shell. So that's 16 and 6 gives me 22 electrons needed. Okay, from that I'm going to subtract the number of valence electrons. So for carbon, that was 4. For the 3 hydrogens, that was 3. Oops. And the 1 iodine is 7. So that gives me 14 electrons. So subtract 14 electrons. So my valence. That gives me 8 electrons. Okay. Take that 8 electrons, divide by 2, tells me the number of bonds needed. Okay. So this process here tells me number of bonds needed. Second thing I need to calculate is number of unshared pairs. If I have 14 electrons that are the valence electrons, and I subtract the number of electrons in bonds, which is 8 electrons, that gives me 6 electrons. Divide by 2 gives me 3 unshared pairs. From before, the element in the center is the one that needs to make the most bonds. The other elements go around it kind of on its 4 sides. I knew I need 4 bonds, so that would be, I'm going to do circles. So those are my 4 bonds, and then I have 3 unshared pairs. That's a second approach to doing or drawing Lewis structures. Real quick, I wanted to show you one that has multiple bonds, and we're going to look at the compound C2H4. And we're going to use the process we just used. So the first thing we do is find the number of electrons needed. I have 2 carbons, so I'm going to need 16 electrons for a valence shell for those. I have 4 hydrogens. Each hydrogen needs 2, so that's a total of 8. That's 4. So I need 24 electrons to fill the valence shell. How many valence electrons do I have? Well, for carbon, I have 4 times the carbon. That gives me 8 electrons. 4 times the hydrogen gives me 4, so that gives me 12 valence electrons. I take the 12 valence electrons minus the 24 that I need for bonding, that gives me 12 electrons. Divided by 2, I'm going to have 6 bonds. Second half is to determine the number of unshared. So I take the number of electrons, valence electrons, and that's 12 electrons. And then I have the electrons in bonds. That's 12 electrons. 0 electrons, so I have no unshared pairs. Okay, so I have C2H4. Now, carbon is one of those ones that can have form a chain. The only one I think we'll look at is carbon. Right, so think chain and think symmetry. So if I put an H here, I'm going to have an H here and here, and I'm going to have one here and here. Now, if you look at that, hydrogens are all satisfied and happy, but I only have 1, 2, 3, 4, 5 bonds. I said I needed 6. If I look at carbon, each carbon only has 1, 2, 3 bonds. Well, carbon wants 4 bonds. And this carbon only has 3. He wants 4. We can put another pair, another bond between those two carbons, double bond, and make everybody have a fully filled octet. I have no unshared pairs. I have the correct number of valence electrons, because 2, 4, 6, 8, 10, 12. That's the number of valence electrons, so I didn't add any, which is good. This is the structure for C2H4, right? And we introduced here multiple bonds. We can have single bonds. That's where I have just one pair shared between two atoms. I can have a double bond, which are 2 pairs of electrons shared. Or I can have a triple bond, which is 3 pairs. I guess I'll write 1 pair for the single. Okay? And that's really how to form Lewis structures.